If someone were to ask you this question, which is larger in size, calcium or bromine? Most people, using simple common sense, would simply say bromine. And why would they say that? Because bromine has atomic number of 35, which means it has 35 protons and 35 electrons. So that is what common sense would tell them, that if it has more protons and electrons, then it should be larger. In reality, calcium is actually a lot larger in size than bromine. The question is, why? To answer that question, we will study periodic properties. We will look at atomic sizes, ionization energies, and metallic properties. Let us begin with elements in the same group of the periodic table. And we're going to make use of group 1A as a representative of all the other groups. In group 1A, we have lithium in period number 2. That is why it is represented as 2 energy levels. We have sodium in period number 3. Sodium has 3 energy levels. Potassium in period number 4, 4 energy levels. And rubidium in period number 5, 5 energy levels. Visually, we can immediately see that as you go down the group, the size of the atom will increase. The question is why? As you add more energy levels to the atom, then the size of the atom will increase. So we can simply conclude that as you go down the group in the periodic table, atomic sizes will increase. So atomic size increases down the group. Let us now take a look at elements in the same period of the periodic table. And we are going to make use of period number 2 as a representative of all the other periods. In period number 2, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. But we are only showing up to oxygen right now. All of them, as you can see, have 2 energy levels because they are from period number 2. And in lithium, we have 3 protons inside the nucleus because the atomic number of lithium is 3. In beryllium, the nucleus has 4 protons. In boron, the nucleus has 5 protons. The nucleus of carbon has 6 protons. The nucleus of nitrogen has 7 protons, and the nucleus of oxygen has 8 protons. Let us begin with lithium. Lithium has 2 energy levels, but so are all the others. And they all have 2 electrons in the first energy level. So it's common to all of them. We will ignore the first energy level. Let us now focus on the second energy level. In the second energy level, lithium has only 1 electron. The protons inside the nucleus of lithium will be pulling the electrons outside the nucleus toward themselves, because the law of nature says that unlike charges, should attract. So in lithium, 3 protons will be pulling on this single electron outside the nucleus. In beryllium, we now have 4 protons in the nucleus pulling on the 2 electrons outside the nucleus. In boron, we have 5 protons pulling on the 3 electrons in energy level number 2 in boron. In carbon, the size of the protons has increased to 6, and those 6 protons will be pulling on the 4 electrons outside the nucleus. In nitrogen, 7 protons will be pulling on the 5 electrons in energy level number 2, and in oxygen, 8 protons will be pulling on the 6 electrons in energy level number 2. One thing that is very obvious is that as the pulling strength of the nucleus increases, we have more dents in the diameter of the energy level number 2. That is another way of saying that each additional proton in the nucleus would shrink the size of the atom if they all have the same energy levels. And that is why lithium will be larger in size than beryllium. Beryllium will be larger in size than boron. Boron will be larger in size than carbon, and so on, which means that the direction of increase in atomic size will be towards the left. Atomic size increases from right to the left across the period. That is why, going back to our original question, calcium will be a lot larger in size than bromine, because although calcium has fewer protons and electrons than bromine, calcium would experience less nuclear pull on the same energy level. Let us now take a look at how ionization energy varies in a group and across the period. The first question is, what is ionization energy? The ionization energy of an element is the energy required, which means we have to put in the energy. This process is endothermic. The energy required to remove an electron from an atom of the element if the atom is in the gas state. Let us try to represent this definition as an equation. Let me write a generic element X, and we are adding energy to that element X because it's an endothermic process. When we add energy to element X, it knocks off one electron from element X so that element X becomes a cation and one electron is knocked off. The amount of energy needed to knock off that one electron is the ionization energy. Let us now take a look at how this property varies in the periodic table. Let us first focus on elements in the same group: lithium, sodium, potassium, rubidium. Each of them has only one electron in the outermost energy level. So this is the question: which one will require the most amount of energy to take one electron from, and which one will require the least amount of energy to knock off the outermost electron? If you look carefully at this, you would see that rubidium will require the least amount of energy to knock off one electron from it. And this is the question: why? Why rubidium? The outermost electron in rubidium is very far away from the nucleus. Remember, the nucleus is positively charged. So the nuclear pull on the outermost electron in rubidium will not be as strong as the nuclear pull on the outermost electron in potassium, which means that as we go down the periodic table, the amount of energy we need to put in to take one electron away from the element will be smaller. And conversely, that means as we go up the group, ionization energy will increase. So ionization energy increases up the group. Let us now take a look at how ionization energies would vary across the period. In period number 2, we have lithium, beryllium, boron, carbon, nitrogen, and oxygen on this page. Which one would require the most amount of energy to knock off one electron from? Now, the easiest way to think about this is to first understand that they all have the same number of energy levels, and the nuclear pull on the energy levels are not the same. That is the same thing as if you and maybe your friend are making the same amount of money, but your friend has a dog, has a gun, and always locks his house door, while you don't have a dog, you don't have a gun, and at times you leave the garage door unlocked. That is the situation here. Oxygen has a lot of protons in its nucleus, pulling on the energy level number 2. Lithium, on the other hand, only has 3 protons, pulling on that same energy level number 2. Because the stronger pull on the energy level number 2 in oxygen is stronger, removing an electron from oxygen relative to lithium will be a lot harder. So it will be a lot harder to remove an electron from oxygen than it would be to remove an electron from nitrogen. And it will be harder to remove an electron from nitrogen than it would be to remove an electron from carbon. In a nutshell, ionization energy increases from the left side of the periodic table to the right. So, ionization energy increases from left side of the periodic table to the right across the period. Let us now take a look at metallic properties. The first thing to note about metals is that they readily give out electrons. That is, metals love to give out electrons, which means that a good metal will not require a lot of energy before it can give out an electron. That is the opposite of ionization energy. So what it means to be a good metal is that an element should have low ionization energy. So that is, low ionization energy is equal to good metallic property. Let us now take a look at the periodic trend. Remember that in the ionization energy trends, we said that ionization energy increases up the group, and we said that ionization energy increases from left to right. And we know that low ionization energy is similar to good metallic property, which means that metallic properties will be in opposite trends of ionization energy, because in group 1A, rubidium requires the least amount of energy to give out an electron. So, rubidium will be a better metal than potassium. Potassium will be more metallic than sodium. Sodium will be more metallic than lithium. In a nutshell, metallic properties will increase as you go down the group. Metallic properties increase down the group. For elements in the same period, again, the lower the ionization energy, the more metallic the element will be. Oxygen on this page is the least metallic among the elements because oxygen requires the most amount of energy to give out an electron. So, metallic properties will increase from the right side of the periodic table to the left side of the periodic table. Let us now take a look at some examples. Circle the appropriate atom in each pair. Which is the larger atom between lead and polonium? We will need a copy of the periodic table. Here is lead and here is polonium. So the question is asking us which is larger in size. If you remember the trend for atomic sizes will increase as you go down the group, and atomic sizes will increase from right to the left. So if we are looking at lead and polonium, lead will be larger in size than polonium because lead is closer to the left side of the periodic table, and both lead and polonium are on the same period. So the answer to the first question is that lead is larger. Let us look at the second question. Which is the larger atom between chlorine and selenium? Let us take a look at the periodic table again. This is chlorine and this is selenium. There is one little technicality here. They do not belong in the same group and they do not belong in the same period. So how do we answer this question? We will have to compare both the effects of energy levels and nuclear pools on atomic sizes. So we will look at effect of energy levels and we will look at the effects of nuclear pool. Let us begin with the effects of energy levels. Selenium is on period number 4 in the periodic table. Chlorine is on period number 3. And we know that the more energy levels an element has, the larger the size of the atom of the element. So, on the account of energy levels, selenium should be larger. Let us now take a look at the effect of nuclear pool. We know that if both chlorine and selenium were on the same period, chlorine will experience a lot more nuclear pools because it is closer to the right of the periodic table. The closer you are to the right, the more nuclear pool you will experience. So, on that count, because chlorine would experience more nuclear pools if they were on the same period, chlorine would be smaller in size, which means again selenium is larger. So on both counts, selenium is a larger atom. So whenever you are comparing two elements and they are not in the same group and also not in the same period, you would have to consider the energy levels effects and the nuclear pole effects. Let us now take a look at question number 3. Which has a higher ionization energy? Magnesium or strontium? Let us take a look at the periodic table. On the periodic table, this is magnesium. This is strontium. They belong on the same group. We know that as you go up the periodic table, as you go up the group, the ionization energy will increase, which means that magnesium will have a higher ionization energy. So, magnesium has a higher ionization energy than strontium. Let us take a look at question number 4. Which one will have a higher ionization energy? Copper or phosphorus? Let us take a look at the periodic table. Here is copper and here is phosphorus. They do not belong in the same group. They do not belong in the same period. So we will need to look at energy level effects, and we will need to look at nuclear pool effects. Let us take a look at energy level effects. Copper is in period number 4. Phosphorus is in period number 3. We know that the more energy levels you have, the lower your ionization energy will be, because the electron will be too far away from the nucleus. So, on the account of energy levels, phosphorus will have the higher ionization energy. As far as nuclear pool is concerned, we know that the closer to the right side of the periodic table you are, the more nuclear pool you will experience. So if copper and phosphorus were to belong to the same period, phosphorus will suffer more nuclear pool, and the more nuclear pool you suffer, the higher your ionization energy. So again, phosphorus has a higher ionization energy. So on both counts, phosphorus will have a higher ionization energy. Let us now take a look at metallic properties. Which is more metallic, gold or copper? Let us take a look at the periodic table. Here is gold and here is copper. They belong to the same group in the periodic table. And we know that metallic properties will increase as you go down the group, and it will increase from right to the left. That is metallic property. So, since gold is in period number 6 and copper is in period number 4, gold will be more metallic. So, gold is more metallic. Let us take a look at the last question here. Between nitrogen and silicon, which is more metallic? Let us take a look at the periodic table. On the periodic table, this is nitrogen, this is silicon. They do not belong to the same group, and they do not belong to the same period. So we would need to look at the effects of energy levels and nuclear pool. Let us begin with the effect of energy level. We know that according to the trend here, the more energy levels you have, the more your metallic properties. So on the account of energy levels, silicon will be more metallic. In terms of nuclear pool, the more nuclear pool you experience, the lower your metallic properties. So, on the account of nuclear pool, silicon is again more metallic. So on both counts, silicon is more metallic.